October 21st, 1948. Inside a Dayton hotel conference room, Air Force Colonel Pete Worden stared at 5 Boeing engineers who had just presented their latest bomber design. 6 propeller engines, straight wings, everything the military had requested. Worden pushed the blueprints aside and said 4 words that would change aviation history. "Give me an all-jet bomber." The engineers worked through the weekend with nothing but slide rules and hotel stationery. By Sunday night, they had 33 pages of calculations and a 14-inch balsa wood model that promised to fly 500 miles per hour with an 8,000-mile range. It was supposed to be the future of American air power. 40 years later, that weekend creation, the B-52 Stratofortress, still flies combat missions over Afghanistan and Iraq. Meanwhile, the $2 billion B-2 Spirit stealth bomber, built with revolutionary technology and computer-controlled everything, sits grounded in climate-controlled hangars. The most advanced aircraft in human history has a 30% mission-ready rate. The 1950s bomber built with cables and pulleys? 80%. Sometimes the oldest technology wins. The fluorescent lights in the Hotel Van Cleve's conference room cast harsh shadows across the polished mahogany table as Colonel Pete Worden examined the blueprints one final time. Boeing's latest turboprop bomber proposal sprawled across the surface, 6 Allison T-40 engines, straight wings spanning 160 feet, a design that represented 18 months of careful engineering and meticulous cost analysis. The 5 Boeing engineers seated across from him had flown in from Seattle expecting approval for their Model 462 design, confident they had delivered exactly what the Air Force's request for proposal demanded. George Scherer, Boeing's chief of preliminary design, adjusted his wire-rimmed glasses and pointed to the performance specifications. "Colonel, the 462 meets every requirement: 450 mile-per-hour cruise speed, 5,000-mile combat radius, 10,000-pound bomb load. We can have the first prototype flying within 30 months. Art Carlson nodded in agreement, his mechanical pencil tapping against a stack of weight and balance calculations that had consumed weeks of slide rule computations. Worden pushed the drawings aside without ceremony. "Forget propellers," he said, his voice cutting through the afternoon stillness of downtown Dayton. "Give me an all-jet bomber." The silence that followed stretched for nearly 30 seconds. Ed Wells, Boeing's vice president of engineering, leaned forward in his chair. "Colonel, with respect, an all-jet heavy bomber would require at least 8 engines to generate sufficient thrust. The fuel consumption alone would cut the range in half. The structural weight—" "I didn't ask for a lecture on aeronautical engineering," Worden interrupted. "I asked for an all-jet bomber. Can you build one or not?" Scherer exchanged glances with von Blumenthal, Boeing's structures chief. Both men had spent their careers pushing the boundaries of aircraft design, but this request challenged fundamental assumptions about long-range bombing missions. Jet engines in 1948 consumed fuel at nearly twice the rate of turboprops. The mathematics seemed insurmountable. "We'll need time to run the numbers," Wells said carefully. "The propulsion requirements alone." "You have until Monday morning," Worden said, standing to collect his briefing materials. "The Strategic Air Command needs a bomber that can reach targets 8,000 miles away and return. Speed matters more than fuel economy. The Soviets are developing surface-to-air missiles faster than our intelligence estimates predicted." The door closed behind Worden with a soft click, leaving the 5 engineers staring at blueprints that had suddenly become worthless. 18 months of design work reduced to expensive scratch paper by a 4-word directive from a colonel who understood strategic necessity better than engineering constraints. Scherer was the first to speak. 8 Pratt & Whitney J-57s, 4 twin-pod nacelles under swept wings. His voice carried the enthusiasm of a man who had just glimpsed a solution to an impossible problem. If we use the swept-wing data from captured German research, we can maintain structural integrity at higher speeds. Carlson began sketching on hotel stationery, his pencil moving with practiced precision. Gross weight around 480,000 pounds. Empty weight maybe 160,000. That leaves 320,000 for fuel and payload. The numbers flowed from his mechanical calculator with rhythmic precision, each calculation building toward a design that existed only in theory. By Saturday evening, the hotel room had transformed into an impromptu engineering laboratory. Mechanical calculators covered every surface, their brass gears clicking steadily as the engineers refined thrust-to-weight ratios and fuel consumption curves. Wells worked through structural load calculations, while Blumenthal computed wing stress patterns, both men drawing on decades of experience designing aircraft that had never been attempted at this scale. The breakthrough came Sunday morning when Scherer solved the range equation. If we mount the engines in pods separate from the wing structure, we reduce weight and improve maintenance access, he announced, sketching rapidly on a fresh sheet of stationery. Independent fuel systems for each engine pair, complete redundancy, lose half the power plant and still maintain flight. The mathematical elegance of the solution became apparent as the weekend progressed. 8 turbojet engines producing 10,000 pounds of thrust, each would generate 80,000 pounds of total thrust, sufficient to lift a bomber weighing nearly 500,000 pounds. Swept wings angled at 35 degrees would maintain structural integrity at speeds approaching 600 miles per hour. Most importantly, the fuel capacity would support an 8,000-mile combat radius with a 70,000-pound bomb load. By Sunday night, 33 pages of calculations supported a design that seemed to violate every conventional wisdom about heavy bomber construction. Art Carlson had carved a 14-inch balsa wood model that captured the essential proportions: long fuselage, swept wings, twin-pod engine nacelles suspended beneath the wing structure like streamlined fuel tanks. The model weighed less than 2 pounds, but it represented a revolution in strategic bombing capability. Wells reviewed the final specifications one last time before sealing the proposal documents. Maximum speed, 500 miles per hour at 35,000 feet. Service ceiling, 50,000 feet. Combat radius with maximum bomb load, 4,500 miles. The numbers exceeded every requirement Worden had specified, achieved through engineering principles that prioritized reliability over complexity. The weekend that began with rejection had produced an aircraft design that would define American strategic air power for decades. What none of the 5 engineers could predict was that their balsa wood model represented more than a revolutionary bomber. It embodied a design philosophy that would prove more durable than the sophisticated technologies that would eventually challenge it. Monday morning arrived with October sunshine streaming through the hotel windows, illuminating calculations that would soon reshape the global balance of power. The Boeing plant in Seattle stretched across 4 million square feet of concrete and steel, its assembly bays echoing with the rhythmic hammering of rivets and the whine of precision machine tools. By 1952, the weekend hotel room calculations had evolved into the most complex aircraft manufacturing program in aviation history. Ed Wells walked the production line each morning at 7 sharp, his engineer's eye cataloging every detail of the emerging B-52 prototype. The aircraft, taking shape on the assembly floor, bore little resemblance to any previous bomber. 8 Pratt & Whitney J57 turbojet engines hung in 4 twin-pod nacelles beneath wings, swept at 35 degrees, each engine producing 10,000 pounds of thrust through individual fuel and electrical systems. Wells had insisted on complete redundancy. No single component failure could bring down the aircraft. The flight control system relied on cables and pulleys, mechanical linkages that had proven reliable since the Wright brothers first flew at Kitty Hawk. "Keep it simple," Wells told his engineering staff during their weekly design reviews. "A pilot should be able to fly this airplane when everything else fails." The philosophy permeated every system aboard the B-52. Analog instruments, mechanical flight controls, hydraulic systems with manual backup, no computer dependencies, no electronic vulnerabilities that enemy jamming could exploit. Technical Sergeant Robert McKenzie understood the aircraft's revolutionary design better than most engineers. As chief of maintenance for the prototype testing program, he spent 14-hour days crawling through the B-52's internal structure, memorizing every wire run and hydraulic line. The 8 independent engine pods fascinated him. Each power plant operated as a separate system with its own fuel supply, electrical generation, and control mechanisms. If we lose 3 engines on one side, Mackenzie explained to his maintenance crew, she can still fly home on 5. The observation would prove prophetic during the next decade of combat operations, but in 1952 it represented theoretical redundancy that no other bomber possessed. The B-36 Peacemaker relied on 6 reciprocating engines and 4 jets in a single wing structure. Engine failure meant catastrophic power loss. The B-47 Stratojet mounted 6 engines in 2 wing root nacelles. Damage to one engine could destroy its paired companion. The first combat test came 13 years later in the humid jungles of Southeast Asia. Operation Arclight launched on June 18, 1965, when 30 B-52F Stratofortresses departed Andersen Air Force Base on Guam for a 12-hour mission to strike suspected communist supply routes near Ben Cat District in South Vietnam. Each aircraft carried 66 750-pound bombs in internal weapon bays designed for nuclear weapons but reconfigured for conventional ordnance. The formation approached the target area at 30,000 feet, flying in cells of 3 aircraft separated by precise intervals that maximized bombing effectiveness while minimizing collision risk. 2 bombers collided during the final approach, the only combat losses of the mission, but the remaining 28 aircraft delivered their payloads with devastating accuracy. The massive explosions carved rectangular patterns of destruction through triple canopy jungle. Each bomb crater precisely spaced according to ballistic calculations performed by analog computers aboard the aircraft. Mission-capable rates during Vietnam operations averaged 75%, a figure that exceeded Air Force expectations for sustained combat operations. B-52 crews flew missions lasting 14 hours, their aircraft functioning reliably in tropical humidity that corroded electronic systems and mechanical heat that warped precision components. The simple engineering philosophy that Wells had championed proved itself under conditions the Boeing engineers had never anticipated. 20 miles southwest of Los Angeles, in a converted Ford automobile plant surrounded by razor wire and armed guards, a different philosophy guided aircraft development. Northrop's Advanced Technology Bomber program operated under security classifications that required polygraph examinations for workers and background investigations for suppliers. Components arrived at the Pico Rivera facility in unmarked trucks during overnight hours, their true purpose concealed by contract numbers that revealed nothing about their ultimate application. Dr. John Cashin directed the stealth technology development with the precision of a theoretical physicist translating mathematical concepts into physical reality. The Advanced Technology Bomber, designated B-2 Spirit in 1981, represented the complete opposite of B-52 design philosophy. Fly-by-wire flight controls replaced mechanical linkages. Composite materials replaced aluminum structure. Computer processors governed every system from engine operation to weapons delivery. "We're not just building an airplane," Cashin explained to his engineering staff during classified design reviews. "We're building a computer that flies." The B-2's revolutionary stealth characteristics required continuous curved surfaces that deflected radar beams in calculated directions, structural materials that absorbed electromagnetic energy, and engine inlets that concealed turbine blades from ground-based tracking systems. The complexity extended beyond aerodynamics into manufacturing processes that demanded tolerances measured in thousandths of inches. Radar-absorbing coatings required application in climate-controlled environments with humidity levels maintained within 2% variations. Assembly workers wore special clothing to prevent contamination that could compromise stealth characteristics. Quality control inspections used laser measurement systems that detected surface irregularities invisible to human observation. Each B-2 Spirit would cost $737 million to manufacture, with total program expenses reaching $44 billion for 21 operational aircraft. The unit cost exceeded the gross domestic product of most nations, justified by technological capabilities that promised to revolutionize strategic warfare. Pentagon planners envisioned B-2 bombers penetrating Soviet airspace undetected, striking critical targets with nuclear precision, and returning safely to American bases. The stealth bomber represented everything the B-52 was not: sophisticated instead of simple, revolutionary instead of evolutionary, computer-dependent instead of mechanically reliable. Two aircraft designed 30 years apart, embodying completely opposite engineering philosophies, would soon compete for the same strategic mission under conditions neither design team had fully anticipated. The classified briefing room at Edwards Air Force Base hummed with quiet tension on July 17, 1989, as test pilot Bruce Hines completed his pre-flight checklist for the most expensive aircraft ever constructed. The B-2 Spirit sat on the tarmac like a geometric puzzle carved from gray composite materials, its flying wing design defying conventional notions of aircraft appearance. No vertical surfaces, no sharp angles, every curve calculated to deflect radar beams away from ground-based tracking systems. Hines guided the revolutionary bomber through its maiden flight with the precision of a surgeon performing experimental procedures. The fly-by-wire control system translated his stick inputs into electrical signals that computer processors converted into control surface movements, each adjustment filtered through software algorithms designed to maintain stability in an aircraft that was aerodynamically unstable by design. "She flies like a fighter," Hines reported to ground control after completing the first hour of flight testing, his voice carrying amazement at the bomber's responsiveness, despite weighing 170,000 pounds, empty. Pentagon planners projected that 132 B-2 Spirit bombers would replace the entire B-52 fleet by 2000, transforming American strategic nuclear doctrine through technological superiority that Soviet air defense systems could not counter. Each stealth bomber possessed radar cross-sections smaller than hummingbirds, achieved through continuous curved surfaces and radar-absorbing materials that cost more per pound than gold. The aircraft could penetrate the most sophisticated surface-to-air missile networks undetected, strike targets with precision-guided nuclear weapons, and return to American bases without enemy forces knowing they had been attacked. The confidence permeating Air Force strategic planning reflected genuine technological breakthroughs that bordered on science fiction made real. Stealth technology represented 15 years of classified research into electromagnetic physics, materials science, and computational fluid dynamics that had produced aircraft invisible to radar systems costing billions of dollars to develop and deploy. Soviet SA-10 surface-to-air missiles could track and destroy any conventional aircraft within 300 miles, but their guidance radars would see nothing when B-2 bombers approached their targets. While Northrop engineers celebrated their triumph over the laws of physics, the supposedly obsolete B-52 Stratofortress prepared for its most demanding combat test since Vietnam. Operation Desert Storm commenced on January 17, 1991, when 7 B-52G bombers launched from Barksdale Air Force Base in Louisiana for a mission that would establish new records for strategic bombing operations. The target: Iraqi command and control facilities protected by some of the most sophisticated air defense networks outside the Soviet Union. The 7 bombers flew 14,000 miles round-trip over 35 hours, their crews sustained by coffee, sandwiches, and the mechanical reliability of aircraft systems designed 4 decades earlier. Each B-52G carried 12 AGM-86C cruise missiles, precision-guided weapons that could strike targets with conventional warheads, while keeping the launch aircraft beyond range of enemy surface-to-air missiles. The mission profile represented strategic bombing at its most sophisticated, long-range precision strikes, coordinated with satellite navigation and real-time intelligence updates. Navigation systems aboard the aging bombers had been upgraded with global positioning system receivers, but the fundamental aircraft structure remained unchanged from Ed Wells's original design philosophy. Mechanical flight controls responded to pilot inputs without computer intervention. 8 Pratt and Whitney J57 engines operated independently through separate fuel and electrical systems. Analog instruments provided flight information that remained functional in electromagnetic pulse environments where digital displays would fail completely. The cruise missile launches commenced at 0300 hours Baghdad time, 12 weapons separating from each bomber at precise intervals, calculated to overwhelm Iraqi air defense radars through simultaneous arrivals from multiple vectors. 84 cruise missiles struck their assigned targets with 95% accuracy, destroying communication centers, radar installations, and command bunkers that coordinated Iraqi military operations. The B-52 crews monitored weapon releases through mechanical systems that had functioned reliably since the Eisenhower administration. 0 bomber losses. Mission-capable rate, 75%. Total flight time, 35 hours without mechanical failures that prevented mission completion. The performance statistics validated engineering decisions made in Seattle hotel rooms during the Truman presidency, proving that mechanical reliability could achieve strategic objectives more effectively than technological sophistication that remained unproven in combat conditions. Air Force maintenance records from Desert Storm revealed operational realities that contradicted conventional wisdom about military technology advancement. B-52G aircraft, averaging 30 years of service, achieved higher mission-capable rates than B-1B bombers that had entered service only 5 years earlier. The newer aircraft required specialized maintenance procedures and climate-controlled storage that limited deployment flexibility, while the older bombers operated from forward bases using standard aircraft hangars and conventional maintenance equipment. The contrast became more pronounced when classified performance assessments compared B-52 operations with projected B-2 capabilities. Each Stratofortress could deliver 70,000 pounds of conventional ordnance using weapon systems that cost $20 million to upgrade. Each Spirit bomber could carry 40,000 pounds of precision weapons using stealth technology that cost $2.13 billion per aircraft to develop and manufacture. Operational costs revealed even starker differences. B-52 flight operations consumed $70,000 per hour, including fuel, crew wages, and routine maintenance. B-2 flight operations required $130,000 per hour, plus specialized hangar facilities that maintained precise temperature and humidity levels to protect radar-absorbing coatings from environmental degradation. The most telling comparison involved maintenance requirements that determined how many aircraft could remain operational during sustained combat operations. Each B-52 required 20 hours of maintenance for every flight hour, work that qualified mechanics could perform using standard tools and replacement parts available through normal supply channels. Each B-2 required 60 hours of maintenance for every flight hour, including specialized procedures that demanded climate-controlled environments and technicians trained in composite materials and stealth coating application. By 1991, the revolutionary stealth bomber program faced strategic irrelevance that no amount of technological sophistication could overcome. The Soviet Union had dissolved, eliminating the primary threat that justified B-2 development costs and operational complexity. The aircraft designed to penetrate the most advanced air defense systems in history would instead face missions that aging B-52 bombers could accomplish more efficiently and reliably. The telephone call that ended the most expensive military aircraft program in American history lasted exactly 4 minutes and 37 seconds. President George H.W. Bush sat in the Oval Office on a cold December morning in 1991, listening to Defense Secretary Dick Cheney explain why the B-2 Spirit bomber program would be terminated at 21 aircraft instead of the planned 132. The Soviet Union had officially dissolved 3 weeks earlier, eliminating the strategic threat that justified spending $44 billion on stealth technology designed to penetrate Moscow's air defense network. "The mission no longer exists," Cheney said, his voice carrying the weight of a decision that would affect thousands of defense contractor employees and reshape American strategic aviation for decades. The B-2's revolutionary stealth capabilities had been optimized for a specific enemy, sophisticated Soviet surface-to-air missile systems defending high-value targets across 11 time zones. Without that threat, the aircraft's technological sophistication became an expensive solution to a problem that had vanished overnight. Congressional Budget Office analysts had been preparing devastating assessments of B-2 operational costs since the program's first flight tests revealed maintenance requirements that exceeded even pessimistic projections. Each Spirit bomber demanded 60 hours of specialized maintenance for every flight hour, work that could only be performed in climate-controlled hangars by technicians trained in composite materials and radar-absorbing coating application. The stealth coatings themselves degraded when exposed to sunlight, moisture, or temperature variations outside narrow parameters, requiring complete aircraft storage in facilities that cost millions of dollars to construct and maintain. Representative John Kasich, chairman of the House Budget Committee, had obtained classified maintenance reports that painted an alarming picture of operational reality. Mission-capable rates for the B-2 fleet averaged 30% during peacetime training operations, meaning that only 6 or 7 aircraft could fly combat missions at any given time out of 21 total bombers. The remaining aircraft sat grounded for coating repairs, software updates, or structural maintenance that required specialized equipment unavailable at forward operating bases. The contrast with B-52 operations became impossible to ignore as Pentagon planners examined actual performance data rather than theoretical projections. Stratofortress bombers achieved 75 to 80% mission-capable rates using maintenance procedures that any qualified aircraft mechanic could perform with standard tools and replacement parts. The 40-year-old aircraft operated from conventional military bases worldwide, requiring only routine aircraft hangars and normal fuel supplies to sustain continuous combat operations. Unit cost calculations revealed the full scope of the B-2's economic inefficiency. Each Spirit bomber cost $2.13 billion to develop, manufacture, and deploy, enough money to purchase 105 F-16 fighter aircraft or maintain the entire B-52 fleet for 5 years. The stealth bomber's payload capacity of 40,000 pounds compared unfavorably with the Stratofortress's 70,000-pound maximum load, meaning that fewer weapons could be delivered at dramatically higher cost per sortie. Operational limitations extended beyond economics into tactical flexibility that determined combat effectiveness under real-world conditions. B-2 bombers required specialized support equipment that filled multiple cargo aircraft, limiting deployment to major airbases with extensive infrastructure and climate control systems. The aircraft could not operate from austere forward bases or conduct rapid deployment missions that characterized modern military operations. Dr. John Cashin watched his life's work dissolve in congressional hearing rooms where politicians demanded explanations for cost overruns and performance shortfalls that had been classified for security reasons. The stealth technology functioned exactly as designed: radar cross-sections smaller than birds, electromagnetic signatures undetectable by the most sophisticated tracking systems, aerodynamic performance that exceeded specifications. But the enemy the technology had been designed to defeat no longer existed, and the missions it could perform could be accomplished more efficiently by aircraft costing 1% as much to operate. Master Sergeant Linda Torres had spent 15 years maintaining B-52 bombers at Minot Air Force Base, watching her aircraft achieve operational readiness rates that defense contractors promised for their revolutionary replacements. Her maintenance crews could repair battle damage using spare parts carried aboard the aircraft and tools available at any military facility worldwide. Combat-proven systems that had functioned reliably since the Korean War continued operating in desert heat, Arctic cold, and tropical humidity that grounded more sophisticated aircraft. Those computer jockeys building the B-2 forgot something, Torres explained to visiting Pentagon officials during a 1995 inspection tour. When your fancy electronics fail at 30,000 feet over enemy territory, you want cables and pulleys you can fix with a screwdriver and some wire. Her crews demonstrated the principle by performing engine changes on B-52s, using equipment that had been standard military issue since World War II, completing maintenance tasks in hours rather than the days or weeks required for comparable work on stealth bombers. The final vindication came through combat operations that neither aircraft's designers had anticipated. Operation Enduring Freedom commenced in October 2001, with B-52H bombers flying from Diego Garcia to strike Taliban and al-Qaeda targets in Afghanistan, missions lasting up to 44 hours with multiple air-to-air refueling operations. The aircraft delivered precision-guided conventional weapons with accuracy that matched the most advanced targeting systems while maintaining operational tempos that would have been impossible with more complex aircraft. Pentagon maintenance statistics from the first year of Afghan operations revealed performance gaps that could no longer be ignored or explained by technological immaturity. B-52H mission-capable rates averaged 80.5% despite continuous combat operations in harsh environmental conditions. B-1B bombers, introduced 20 years later with more sophisticated systems, achieved 53.7% readiness. B-2 Spirit aircraft managed only 30.3% availability while conducting training missions from climate-controlled facilities in Missouri. The numbers told a story that defense analysts had been reluctant to acknowledge throughout the previous decade of procurement battles and budget hearings. American strategic bombing capability depended more on operational reliability than technological sophistication, more on sustained availability than revolutionary performance, more on mechanical simplicity than computer-controlled complexity. The aircraft designed with 1940s technology and built during the 1950s had achieved what $44 billion of stealth development could not: reliable, cost-effective global combat operations that could be sustained indefinitely under conditions that would ground more advanced alternatives. The maintenance hangar at Whiteman Air Force Base fell silent every time a B-2 Spirit bomber experienced what technicians euphemistically called coding degradation events. The radar-absorbing materials that made the aircraft invisible to enemy tracking systems proved devastatingly vulnerable to conditions that conventional aircraft weathered without concern. Sunlight caused chemical breakdown in the stealth coatings. Moisture penetrated microscopic gaps that expanded into structural problems, requiring complete panel replacement. Temperature variations outside narrow parameters triggered delamination that compromised the bomber's primary tactical advantage. Technical Sergeant Maria Santos had supervised B-2 maintenance operations since 1997, documenting failure patterns that defense contractors attributed to normal operational wear, but which her crews recognized as fundamental design limitations. Each stealth bomber required complete hangar storage between missions, climate control systems that maintained temperature within 2 degrees and humidity within 5%, and specialized coating repairs that consumed hundreds of man-hours using materials costing thousands of dollars per gallon. The maintenance logs told a story of technological sophistication undermined by operational reality. Software glitches grounded the fleet repeatedly as computer processors failed to integrate properly with flight control systems, navigation equipment, and weapons delivery mechanisms. The fly-by-wire control system that made the aircraft flyable also made it completely dependent on electronic components that proved less reliable than the mechanical linkages they replaced. A single processor failure could prevent mission completion, while backup systems required additional computers that multiplied potential failure points. Unit cost calculations revealed the full scope of operational inefficiency that had been concealed during development and procurement phases. Each B-2 Spirit cost $130,000 per flight hour, including fuel, crew wages, specialized maintenance, and facility overhead, nearly double the operating cost of conventional bombers performing identical missions. The aircraft designed to revolutionize strategic warfare had become too expensive to use, except under circumstances that justified risking $2.13 billion of taxpayer investment. Meanwhile, the supposedly obsolete B-52 Stratofortress underwent modernization programs that enhanced combat effectiveness while maintaining the fundamental reliability that had sustained continuous operations for 4 decades. GPS navigation systems replaced celestial navigation equipment, but mechanical flight controls remained unchanged. Digital displays provided enhanced situational awareness, but analog backup instruments ensured mission completion if electronic systems failed. Precision-guided munitions capability allowed conventional weapons to achieve accuracy previously reserved for nuclear strikes. The upgrade costs totaled $20 million per aircraft, exactly 1% of a B-2's procurement price. Boeing engineers approached the modernization with the same philosophy that Ed Wells had championed during the original design process: enhance capability without compromising reliability, add sophisticated systems without creating sophisticated vulnerabilities, integrate new technology while preserving proven mechanical solutions that functioned independently of electronic support. Operation Enduring Freedom provided the ultimate test of both aircraft philosophies under combat conditions that neither design team had fully anticipated. B-52H bombers began flying missions from Diego Garcia in October 2001, conducting the longest continuous bombing campaign in aviation history against Taliban and al-Qaeda targets scattered across Afghanistan's mountainous terrain. Mission duration averaged 18 hours, with some flights extending beyond 40 hours through multiple air-to-air refueling operations. The Stratofortress aircraft delivered precision GPS-guided joint direct attack munitions with accuracy that matched the most sophisticated targeting systems while maintaining operational tempos that would have been impossible with more complex aircraft. Each bomber could carry 16 2,000-pound JDAMs internally, plus additional weapons on external pylons, providing payload flexibility that exceeded specialized stealth bombers designed for nuclear missions. The conventional weapons struck caves, bunkers, and vehicle concentrations with precision that eliminated the need for nuclear firepower while minimizing collateral damage. Classified Air Force maintenance statistics from the first year of Afghan operations documented performance comparisons that defense analysts had been reluctant to acknowledge publicly. B-52H mission-capable rates averaged 80.5%, despite continuous combat operations in desert conditions that corroded electronic components and mechanical systems. B-1B Lancer bombers, introduced 20 years later with more sophisticated avionics, achieved 53.7% readiness under identical operational conditions. B-2 Spirit aircraft managed only 30.3% availability while conducting training missions from climate-controlled facilities that protected stealth coatings from environmental damage. The contrast became even more pronounced when examining sustained operational capability that determined strategic effectiveness during extended combat campaigns. B-52 squadrons maintained multiple aircraft airborne 24 hours per day for weeks at a time, their crews rotating through missions that taxed human endurance more than mechanical reliability. The 8 independent engines provided redundancy that allowed continued flight operations despite battle damage or mechanical failures that would force other aircraft to abort missions. Colonel Sarah Mitchell assumed command of the 2nd Bomb Wing at Barksdale Air Force Base in 2008, overseeing B-52 operations that spanned 3 generations of aircrew and 4 decades of technological evolution. Her pilots included officers born during the Clinton administration flying aircraft manufactured during the Eisenhower presidency, a generational span that reflected the Stratofortress's unprecedented service longevity. The bombers had outlasted the Soviet Union they were designed to attack, the Cold War they were built to fight, and multiple replacement programs intended to make them obsolete. We're proving that sometimes the simplest solution is the best solution, Mitchell explained to visiting Pentagon officials during a 2010 inspection tour. Her maintenance crews demonstrated the principle by performing engine changes, using equipment that differed little from tools used during the aircraft's initial deployment, completing repairs that kept 40-year-old bombers more mission-ready than billion-dollar alternatives that required specialized facilities and trained technicians unavailable at forward operating bases. The final vindication came through mathematical certainty that no amount of political pressure could dispute. By 2010, B-52 bombers had flown over 500,000 combat hours since 9/11, delivering more ordnance with higher reliability rates than any other aircraft in the Air Force inventory. Mission-capable rates consistently exceeded 75% using maintenance procedures that any qualified mechanic could master and spare parts available through standard military supply channels. The aircraft, designed with slide rules and built with rivets, had achieved what computer modeling and revolutionary materials could not: sustained global combat operations that functioned reliably when lives depended on mechanical systems performing exactly as designed, regardless of environmental conditions, enemy action, or technological obsolescence that had claimed more sophisticated alternatives.